Today we will discuss about some activities related to magnetic effect of electric current. Myself, Shubhamurthy, Vegetable Physics, JRB Chikmagalur. Now, let us consider some of the magnets, such as one is a bar magnet, other one is horseshoe magnet, other one is a compass needle. So these are the three different types of artificial magnets which we are using in our day-to-day life for different applications. This bar magnet, if I take, it is having two poles. One is north pole, where we are having a dot, white dot over the pole region. So this represents north pole, and there is no such mark on the any side of the pole, that is taken as south pole. So every magnet is associated with two poles. One is north, another one is south. How to say that it is a north pole? Just take a bar magnet itself and suspend it freely in a air. So this is just stand still in a particular orientation, which is representing geographic north south. Means the pole region which is directed towards geographic north is taken as geographic north pole or magnetic north pole, and the region which is directed towards geographic south is taken as magnetic south pole. So if I cut this magnet into pieces, then each magnet will have their own characteristics. They behave like two separate magnets, but the magnetic field or the magnetic strength will be reduced. We can say it is off. If I get it to exact 2 off, then I can say that it will become off. The magnetic strength will become off of that of the initial. So this is a special type of magnet, which is called horseshoe magnet, in which I have north as well as south pole towards same direction, unlike bar magnet. So this horseshoe magnet is used in Fleming's left-hand rule applications or electric motors, electric generators like this. We have compass needle, which is used in finding the direction. So we have three different magnets which are prepared by man, that is artificially prepared for our day-to-day purposes. When I just hammer this magnet, or if I avoid to fall from my height, or if I give temperature for it or heat it, then it will lose its magnetic property. So always we should take care that whenever we are handling a magnet, we should handle it with care. Now let us study the magnetic field lines. That is how the magnetic force is exerted by the magnet in its surrounding. Here we have bar magnet, in which the magnetic north is directed towards geographic north and magnetic south is directed towards geographic south. And you notice carefully the other magnets or compass needles which are aligned in a circular path here. Each pointer or each needle in each and every compass needle is directed in its own way, or they are being. So this here the north pole, that is marked with the red, it is moving away from the magnetic north. Whereas here the north pole is moving towards the south pole, because the basic property of magnet says that like poles repel each other, unlike poles attract each other. So since these pointers are all representing the north pole here, so these north pole are directed towards the south pole. Okay, so hence we are going to form a curve here. So it is usually 3-dimensional, but since we are making over the plane, we are getting a 2-dimensional diagram. But the magnetic lines or magnetic lines of force are acting in all the directions. So hence we can notice that when I join these heads or the point tips and mark them, and if I join them, they will form a concentric circles, which we are going to see in this diagram. Here we are seeing the compass needle, in which compass needle is directed towards geographic north-south. Okay. So this compass is useful in determining the direction of the geographic north, south, east, west. Okay. Now we are having a bar magnet which is kept in the direction of geographic north-south, facing the north pole of the bar magnet towards geographic north and south towards geographic south direction. Let me spread the iron dust or iron powder. Let us see what happens, how they are going to be aligned. So you can just see here, the iron dust is aligning in such a way that it is going to form a oval shape or circular shape, in which the maximum amount of iron dust is accumulated at the poles, whereas at the center it is very light. It shows that the pole strength at the poles, the magnetic field line strength is more compared to the center or the middle, and is going to form a curved structure. And moreover, this curved structure is going to originate from one pole and end at another pole. So for our convention, we will take it as from north pole to south pole. Okay. So the magnetic field lines are emerging from north and ending at south. This is our convention. And in the absence of any neighboring poles, they will extend up to infinity. Means they will travel up to infinity. So the magnetic field lines capable of traveling up to infinity. Because you can see here, when I am seeing at the center, so there is no such curves are being found here. Instead, it is going to be a straight line. Okay. In the same way, let us consider the horseshoe magnet and let us study how the magnetic field lines are being formed here. So you can just notice here, the horseshoe magnet is having two poles, one is north, other one is south, and as you are noticing in the bar magnet, here also we are going to find the curved lines which are originating from north and ending at south, means they are forming a curved lines. So most of the iron dust is accumulated at the poles, whereas at the center it is very lightly arranged. So that means the pole strength is again here also is maximum at the poles, whereas it is weak at the middle or center. So an experiment, you have noticed that the iron fillings or the iron dust is aligned in a particular pattern or in a particular line which is not intersecting here. So that means they are not going to intersect. There is one magnetic field lines will not intersect with another magnetic field line, because each magnetic field line represents the direction of tangent, the direction of magnetic force or magnetic field when I draw a triangle to the curve. Okay, that means at the poles the magnetic field is very stronger compared to the middle part or the central part. Here we are having an illustrated diagram in which we are going what we are going to present on the plane of paper. Even though the magnetic field lines which are originated here or which are going to form in a 3 dimension, I cannot represent the 3 dimensions, so we will just represent 2D plane such that the magnetic field lines are emerging from north and they are going to end at south pole, and at the center they are going to travel up to infinity. So you can just notice here a straight line towards south and north pole which are traveling to infinity, and that means they are going to form a large curve, okay, before entering into the south pole. And the other curve which are very close, they are being drawn curve, okay, because they are very near to each other. So this is how we are going to write the magnetic field lines over the plane of paper, even though it is 3 dimension. And one more thing, as I noticed here, no two magnetic field lines are intersecting. Okay, they are having their own different path, because the tangent drawn or the straight line drawn to these curves will represent the magnetic force or magnetic field. Now let us study how the magnetic field is useful in studying what is the effect of current. Okay, that is Oyster experiment. So we will talk about Oyster experiment here. So in this Oyster experiment, we are going to see that when a current carrying conductor is placed close to the compass needle, it undergoes deflection and it changes the change in direction. So here it is, if I take this in a forward bias, then this is in reverse bias, or if this is in anti-clockwise direction and this is in clockwise direction, you can see the direction of compass needle is showing different when we are keeping the current carrying conductor on it, means over the compass needle. So this you will study over the study over the activities. Here we are having a reversing key in which I have this is the positive terminal and this is the negative terminal here. Okay, and we have set up with this arrangement such that I can just change the direction of current as I needed. So here we are having two compass needles in which one is moving in the forward direction, means another is having the direction of current in reverse direction, and I have kept the current carrying conductor over it. Okay, and this is a common compass which I am using here. So let us now study what will happen when I apply the current in anti-clockwise direction. This is the anti-clockwise direction current I am flowing, means I am making the current to move in this way, in the anti-clockwise direction. So carefully observe what is happening in the direction of deflection of the needle here. Now when I just reverse it and I make the current to move in clockwise direction, now again you notice the direction of compass needle here. Now one more experiment we will do in which I am keeping the conductor on downward direction, or I am keeping the compass needle on top of the current carrying conductor, facing the compass needle towards north and south itself. Now let me apply the current in anti-clockwise direction. So you can just notice here the direction of the compass needle is just opposite of the initial, means what I noticed in the initial case. Similarly, when I just apply the clockwise current, here also we will notice that it is going to be initially it is going to what we are noticed the direction that is not going to be there, means it is just opposite of the initial direction. It shows that when a current carrying conductor is kept close to the compass needle, it will experience the magnetic force, or that means the compass needle will undergo deflection. So due to production of magnetic field around the current carrying conductor, there is a deflection in the compass needle. Now this direction of magnetic field produced due to current carrying conductor is explained by this right hand thumb rule, or also called as third rule, because I just take a current carrying conductor. Let's hope that this pen is represented the direction of current carrying conductor. Stretch the right hand thumb in the direction of flow of current and remaining fingers closed. Then it explains that if this thumb is represented the direction of current and the remaining fingers closed, then the closed fingers represent the direction of magnetic field in such a way that they are going to form a concentric circles as I am noticing. So the thumb shows the direction of current, whereas the remaining fingers closed show the direction of circles. So the magnetic field is around the current carrying conductor in a circular form. So this is also we can learn with the help of Maxwell's flow rule and as well as Ampere's swimming rule. Now let us know how the direction of current is going to change using this simple activity. So let us study with this activity how the current carrying conductor will behave in the presence of magnetic needle, means how the magnetic needle is going to show the deflection. So let us consider a reversing key again, with which here it is again representing the anti-clockwise flow of current and here it is representing clockwise direction of current. That means here I am having this conductor in which I am having anti-clockwise, means it is the current is moving in downward direction here. If it is clockwise, the current is moving in upward direction. So let us now go for first anti-clockwise direction and carefully notice the direction of compass needles. So you can just see here the compass needles have got deflection such that it is going in the right hand thumb rule. So I am having a current carrying conductor in this way. So therefore if the current is moving in downward direction here, then what the direction the magnetic field produced surrounding the compass needle, that is how the magnetic needles are going to be deflected here. So when the current is moving clockwise direction, that means the current in this conductor is in upward direction, then we notice that the compass needles are reflecting in a such a way that it is it is forming a concentric circle in such a way that it is going to be reflected around the current carrying conductor. That means I have a upward motion of the current, then the compass needles are going to reflect in the direction as bound by the right hand thumb rule. Again, you just carefully observe it. So when I am having a compass needles and forming concentric circles, when I close the current key such that the current is moving in anti-clockwise direction, that is in downward direction, you can just notice here the compass needle which is highlighted here. Okay, so one is moving towards northeast, another moving towards northwest. Okay, means all the other small compass needles, they are also showing a deflection because they are forming a concentric circles and they are being influenced by the magnetic field produced due to current carrying conductor. In the same way, when I am just allowing the current to flow in clockwise direction, that is here in the conductor the current is moving in upward direction, we notice that this upper compass needle is showing the deflection towards northwest, whereas that of the downward compass needle is showing the deflection towards northeast. Means I have two different directions again. So here also in the small compass needles, we find that the needles are reflected in such a way that they are cooperating the deflection of the two main compass needles. So this is a useful experiment which will explain us how a current carrying conductor will behave in the presence of magnetic field, or means how the magnetic needle is getting influenced with the help of current carrying conductor. So what is in what direction the current is producing magnetic field around it. And you also notice that when I just move away from the center, okay, the deflection is going to be decreased, or the needles which are placed at the corners, they are showing the small deflection because the magnetic field strength is going to reduce as I move from the center. Here we observe, here the battery positive is placed here and negative is placed here, such that the battery is moving in this conductor in an anti-clockwise direction. So when I switch on the key, so you can just see that the magnetic field produced surrounding this conductor is separating the concentric circles, hoping that they are also forming a anti-clockwise direction. Here the loop, when I just see from the top, they are seeing as if they are anti-clockwise direction. On the other side, when the current is moving with the same battery, if I apply the current in clockwise direction here, so the magnetic field is, the current is moving downwards and the magnetic field lines which are drawn, they are forming concentric circles in such a way that they are going to form a clockwise loops. So therefore, there are two different patterns are formed and I am applying the current based on the direction of current here. Okay. So if the current is moving upward direction, the magnetic field lines formed surrounding it is having anti-clockwise direction. Whereas when the current is moving downward direction, the magnetic field surrounding it is forming a clockwise direction, concentric loops. So this is got by right hand thumb rule again. Now let us study Fleming's left hand rule with the help of activity. Here we are having the battery eliminator which is placed having positive terminal connected to this reversing key, and that of the negative terminal is connected to the other side of the reversing key. So I have two terminals here, this is negative, this is positive. So this is a reversing key wherein I can change the direction of current. Now let us take a horseshoe magnet. And place close to the conductor in which current is moving when I switch on the key A, such that, so this is the north pole, here I am having the north pole and this is the south pole. So the current is moving, magnetic field is moving in downward direction, and let us study what is the direction of deflection of the current carrying conductor. So it is inwards, means I have to see that the current is moving in towards me, that is out of the plane. So the magnetic field is moving towards inverse direction. So this is the direction of magnetic field and this is the direction of current. When the current is moving towards me, means out of the plane, it is deflecting. So when I reverse the direction of current towards key B, so you can just notice that the conductor is automatically moving outwards. Means it is showing that when the current is entering into the plane, that is away from me, for the same direction of magnetic field applied, it is moving outwards. Now let us change the direction of current as well as direction of magnetic field also. Now I am interchanging the polarity of the magnetic pole. So now the magnetic field is here, this is representing the north pole. So this part is representing north pole, this part is representing south pole. So therefore the magnetic field line is moving from north to south. Now let us study what will happen now. Okay. So when I apply the current towards A, it is showing outward motion because the direction of magnetic field is changed now. Okay. On the other way, when I apply towards the key B, so the magnetic field, the conductor is going to move inwards because the direction of magnetic field is changed. So hence we can just notice that whenever there is a flow of current in the presence of magnetic field, it will experience a force such that that force is going to act on the conductor and make it to displace. So using this simple experiment, we can explain Fleming's left hand rule. Let us touch first the fingers of our left hand mutually perpendicular to each other, such that the thumb shows towards the direction. The index finger of the forefingers represent the direction of magnetic field, and the middle finger of the center finger represent the direction of current flowing through the conductor. Then the thumb shows the direction of motion experienced or force acting on the conductor. Means here the index finger represent the direction of magnetic field applied, and the central finger or the middle finger represent the direction of current flowing through the conductor. Then the thumb shows the direction of force experienced by the conductor. Hence we have seen that whenever I change the direction of magnetic field or current, we have found that the motion of the conductor was different. So this is a setup we have made in the experiment. Here we are having an offshore magnet having one north pole, which is the direction of magnetic field here, and the current is moving into the plane as I shown in this arrow, and the motion of the conductor is outwards, out of the plane of the offshore magnet. So using a simple experiment setup, we have found that a current carrying conductor will experience force. So these are some of the activities which you have learned. So today we have learned the hoisted experiment, in which we have found that a current carrying conductor will execute magnetic field, that the capacitor kept close to the current carrying conductor will always get deflected. And if I change the direction of current, then it will also change the direction of magnetic field also. Okay, that is what we have noticed. Then we have studied the magnetic field due to current carrying conductor, straight current carrying conductor, in which we found that the magnetic field is forming a concentric circles having at the center the magnetic pole strength is more compared to the neighboring. Okay, means the concentric circular pattern. Then next we have studied the Fleming's left hand rule, in which we found that a current carrying conductor is placed in a uniform electric field. It is experiencing the force such a way that all the three components, magnetic field, current and the motion, all are mutually perpendicular to each other. So this is a simple experiment we can just conduct to study the physics chapters interestingly. Thank you. Thank you everyone.